We're going to continue talking about continuity today. So I believe in the last lesson we talked about discontinuities, which are places where the graph is not continuous, okay? And a real simple, like not super technical definition of continuity is, can you draw the graph in its entirety without picking up your pencil? So like what I just drew, that would be a continuous graph. But if the graph has a hole in it, or if it has an asymptote, the graph is going to break into two or more pieces, and that's when you are not continuous, okay? So mathematically, what does it mean to be continuous? And this is our function definition of continuity at a particular point. There are three pieces to this definition, okay? And it's important that you kind of understand what each one separately is saying, because some of the questions you'll be asked will be, explain why this is not continuous, and you'll have to cite one of these three things, like which one of these three things is not true, okay? So the first thing we need is the function to actually be defined at that point. We need to not have this be an undefined value, okay? So if you have like an asymptote or something sitting at C, then clearly we are undefined because C itself is not a defined value of the function. You also need a limit that exists. And remember, when we say a limit exists, that means the right-handed limit is equal to the left-handed limit. So we need the right hand and the left-handed side to be coming to the same place. And then this is the piece that kind of ties all of that together. That limit that exists needs to be equal to the function point itself. Okay, so all three of those things kind of have to play together here. Okay. So I like to tie all of this together actually with one kind of overarching statement here, and I'm going to just kind of do this and say this is all three of these together in one mathematical statement. I like to say, okay, this means the limit as we approach C from the left is equal to the limit as we approach C from the right. That's basically the second bullet point, right? But then those two things, so that would give you your overall limit, those two things need to be equal to the actual function value, okay? Or I guess that should say f of C, sorry about that. Okay, the function value at point C. So the limit needs to be equal to the point itself. Okay, so before we go on to our examples here, I have a picture that I want to show you, and we're going to kind of talk through some of these pieces here. Hold on, just digging through papers and whatnot. Okay, so let's say I have a graph that looks something like this. I think I can get this whole thing in on the screen. And I just want to show you some different examples of those three pieces. So if I was to ask you about continuity at A, this thing would not be continuous because of that first line, right? F of C is defined. In this graph, F of A is not defined. If I go to this X value, I have no point that goes along with point A, okay? I'm actually going to hop over to point C next. Point C, we have a break in the graph. This is not continuous. The question is why? Well, if I were to take the point exists, F of C exists, it's this point right here. But the next thing is I need a limit. And if I take the limit from the left and the limit from the right, those are landing in two different places. So this does not have a limit at C. So I don't have my limit. So that's an example of item number 2 failing, okay? We don't have item number 2 be true. Well, let's look at B, okay? At B, I have the function defined. I have this point right here. The function is defined. If I asked you for f of b, you would tell me this value right here. I have a limit. So if I come in from the left or if I come in from the right, both of those sides are coming together in the same location. So the limit from the left and the right are the same. So I have a limit. That's great. So I have a limit. I have a function point. The problem is they're not the same, right? The function value is up here and the limit is down here. And so this is an example of violating that third piece where the limit is not equal to the function value. I did throw one other point on here because I just wanted to make sure we talked about what it means to be continuous. Okay, so at D, if I were to ask you for f of D, you would point to this point right here. If I was to ask you for the limit from the left, you would follow along from the left and you would land right here. If I asked for the limit from the right, you would follow along and you would land right here. All three of those converge in this same place. And so that's why we would say that this function is continuous at D. Okay, so let's talk about some of the math there, how we're going to show this mathematically. I've got this crazy piecewise function here for you. Okay, it's a three-way piecewise function. And it says determine whether f is continuous at each value. Now, I want to talk about something because sometimes it's not going to give you the value. Sometimes it's just going to say, you know, find any discontinuities. So I want to make sure we realize that the only place I'm really worried about discontinuities here, because none of these functions have anything in them that would make a discontinuity, like an asymptote. They don't have any denominators, anything like that. But I'm worried about jump discontinuities at -1 and at 2. Okay, those are the only places I'm actually worried about there being a discontinuity. So this question, I already know the answer to it. Okay, at 0, I don't have any discontinuities because there's no way the graph is breaking at 0. However, we're going to talk about how to justify it, so I'll make sure to show you that. Okay, so if I want to check and see if I'm continuous at -1, here's what I really need to find. Turn a little bit here. I need to find, first I'm going to find f of -1. And then I'm going to find the limit at -1, which means I'm going to look at -1 coming in from the left. And I'm going to look at the limit at -1 coming in from the right. And what I want to know is, are all three of these things the same? Okay, so starting with f of -1. -1, I mean, it shows up here and here, but see how I have an equal bar here? That means this is the function that I'm using to work with -1 itself, okay? Because this is where we're equal to -1. So I'm going to say -1 plus 2, and this function value would just be 1. Okay, now I want to know what's happening to the left of -1. Well, to the left of -1, that's this function up here. That's less than -1. That's the left side. So now I'm going to use this top function. And I'm going to say, all right, let's do -1 squared plus 2 times -1 plus 1. Well, this is +1. This is -2, so that makes -1 altogether. And -1 plus 1 makes 0. Okay. Oh, and you know what? I just realized I don't think it actually changes my answer much, but I copied this wrong. This should be a minus. Okay, so let me crunch these numbers again. -1 squared is 1, and then this is -2 times -1, so that's +2. So 1 plus 2 is 3, plus 1 is 4. Okay, so it does change this number, but I can stop right here. Because even if this limit from the right exists, which it does, I know that my function value and my limit aren't going to match, right? And so this is my reason for this function not being continuous. Let me just do the one from the right. From the right, I would use this function here because this is when x is greater than -1. So this is actually going to match the top, okay, because I'm using the same function. But because this one doesn't match the other two, this function is not continuous at -1. Not continuous at -1. And really my issue here is that my limits don't even line up. So I'm just going to say the limit does not exist, which is issue number 2 from our definition. Okay. So all of that kind of goes with problem number 1. Okay, problem number 2, the x equals 0. We sort of already talked about this one, but I want to talk about how I'm going to do the justification. The reason we know for sure 0 is continuous is because 0 lives really comfortably within this range. Okay, so my limit from the left and my limit from the right are all still coming from this equation. I don't have anything weird going on either side. And then my function value itself also falls in this range. So for all three of these things, I would be using this x plus 2 function. Okay? So because those are all going to come out the same, I'm going to say, yes, this graph is continuous at 0. Okay? And I want you to pay a special attention to how I'm justifying. So continuous at 0 because the limit as we approach 0 from the left is equal to the limit as we approach 0 from the right, which is also equal to f of 0. And all of those things come from the x plus 2, so it's just going to be 0 plus 2, which is 2. So all in one mathematical statement, I was able to establish that the limits are equal, they're equal to the function value, and then this is what all of them are actually equal to. Okay, let's check out what's happening here at x equals 2. At x equals 2, I am looking at, again, I want f of 2. I want the limit as x approaches 2 from the left. And I want the limit as x approaches 2 from the right. Okay, I'm going to erase some of my scribbles up here so that these aren't in the way. So when I'm looking at 2, f of 2 is coming from this function here because I have the equal bar there. So this is where I'm going to pull f of 2 from. The left limit, what's happening to the left of 2, that's happening up here. So this is where I'm going to take the left function, this is the middle one. And then the right of 2 is also this function. So we have the right and f of 2 coming from the bottom function. We have the left side coming from that middle function. So I can already see kind of where I could potentially run into an issue, but let's find this. So f of 2, let's see, I dropped my colors here. Trying to make it so it's easier to see. F of 2, I'm pulling from this guy. So I would go 2 to the second power, which is 4. Limit from the left, I said I was pulling from here, so that's 2 plus 2, which is 4. And then limit from the right, I'm also using the 2 to the x, so that's 2 squared, which is 4. And hey, look, they're all the same. Okay, all three of these are the same. So because they're all the same, I'm going to answer this question by saying this graph is continuous. Oh, let's go back to green here. Nope, back to orange. Continuous. And I'm going to say something like I said up here above. I'm going to say limit as x approaches 2 from the left equals the limit as x approaches 2 from the right, which also equals f of 2, and all of those things are equal to 4. Okay, so that's me showing that they're all equal to each other. Those types of questions are very common, so hopefully that made sense. If you do have questions about those, please make sure you ask next time you see me. All right, let's take a look at example 2 here. This one is almost guaranteed to be on the AP test. So we've got a piecewise function. And it says what value of k would make this function continuous? Well, let's think about where do we have to worry about it? Where do we have to worry about it not being continuous? The only place that could happen is right here at -2, because that's where my graph breaks from one piece to the other. Okay? And this is also where my function value will come from. So this will be my left-handed limit and my value. And this will be my right-handed limit. And I need all of that to be equal to each other at -2. And sometimes I actually write that out in a sentence, just so we understand this. For the sake of your notes, that might be helpful. So what we need to have happen is we need that 2 minus x squared to be equal to the bottom half, the 4x plus k, at x equals -2. So we're going to solve for k, but what we have to realize here is that this -2 needs to go in for x. Okay, so my setup here is going to be 2 minus -2 squared equals 4 times -2 plus k. This is going to give me 4, so 2 minus 4 is negative 2. And then I have negative 8 plus k. Add the 8 to the other side, and I get 6 for a k value. So if this value were a 6, these two halves of the function would connect, okay? And if they connect, then we don't have to worry about continuity anymore because my left side and my right side are the same. Okay, that's really what you need to know about continuity. That definition of continuity, I would make sure you have a pretty good understanding of that. That's going to be really useful to you, okay? That's it for today, and I hope you have a great day.